Vibes are good, right? Yeah, those are good. Everybody's here? Anybody need a tie? Everybody's got a tie? Okay. Okay, we'll start.
Good afternoon. We are the CubeSat Deployables project, and today we'll be presenting on our systems requirements review. Our faculty advisor is Me Lee, and our technical reviewer is Ted Nye. The sponsor of our project is the Cal State LA Mechanical Engineering Department. My name is Sala Kim. This is Vimal Patel, Jason Lin, Benjamin Delator, and Andrew Wong. For today's agenda, we will first introduce our project and go over our project management, and then we will cover some of the technical progress we have made thus far. Finally, we'll summarize the key points of this presentation. Now I'll go into the background of our project and go over some of the current deployment systems that relate to our project. So, what is a CubeSat? A CubeSat is a miniature satellite with very specific requirements. CubeSats come in units of 1U. 1U is defined as a 10 by 10 by 10 centimeter cube with a maximum weight of 1.3 kilograms. Now, what is a solar sail? A solar sail is essentially a large reflective mirror that can reflect solar radiation pressure. Solar sails have risen in popularity in recent years as a satellite propulsion method due to their relatively low cost and the fact that they do not require a propellant. Solar sailing uses the momentum by solar radiation pressure force on a solar sail for thrust. A common analogy for solar sailing compares the solar radiation pressure force on a solar sail to the way wind acts on the sail of a sailboat. A previous senior design team came up with an attitude control method that utilizes solar sails. Their method involves 4 independent sails that have the ability to rotate. Rotating the sails will create a force imbalance and in turn create a thrust. The objective of our project is to deploy one of these such sails. Some current solar sail deployment methods for CubeSats include the Light Sail by the Planetary Society, the CNU Sail 1 by Chaminade University, and NASA's NanoSail-D and Solar Scout. However, these designs differ from ours in that they are single sail designs, which means that each section of the solar sail come together to form one sail, whereas ours, as discussed, will have 4 independent sails. In addition, these will be primarily used for thrust or deorbiting. However, aerial density is an important factor for all solar sail applications. Aerial density is defined as the weight of the entire CubeSat, including the solar sail, to the area of the solar sail once it has been fully deployed. In order to have an effective solar sail system, the lowest possible aerial density is preferred. Now, I'll hand it off to Vimal.
Thank you, Sala. Today I'm going to talk to you a little bit about the project management and includes the scope, the deliverables, the project organization, and our schedule. So what is the scope? The scope is to develop a prototype deployment solar sail that allows for rotational use. Basically, in other sense, we'll take our 3U cube and we'll insert a subsystem or a module that includes our boom and our solar sail, which will all deploy synchronizing. Next, I'll talk to you a little bit about our deliverables. It consists of 3 review packages, our final report, weekly agendas, a final prototype wing, and then a prototype deployable solar sail fixture, which will include the boom and the solar sail itself inside, and then an optimal operation manual. Now I'd like to go into our project organization. I'd like to start off with Jason, our student lead. He will be working on our architect hardware. Andrew, that will take care of our boom design and any technical support we may need. Benjamin with any folding methods for the solar sail. Sala with our research. and then me with our electrical components and control systems. And as far as the fall of 2018 semester, we are currently on schedule. We're looking pretty good right now. So with that being said, I'd like to introduce Jason, our student lead.
Thank you very much. So I will introduce the requirements, the conceptual designs, and power function overview of our project. So for our requirements, it is mostly covered by the publications published by NASA. And first, the total chemical energy, it should be less than 100 watts-hour. In our case, it represents how much energy we could put inside our batteries. Second, the maximum dimensions of the CubeSat itself that NASA allow us to deploy through their program should be 30 centimeters height, 20 centimeters wide, and 10 centimeters big. It is exactly the same dimension as 6-unit CubeSat. Third, for the CubeSat bus voltage, it should be exactly 14.8 volts. Fourth, for the mass of CubeSat, it should be less than 12 kilograms. Fifth, for the power output, it should be larger than 100 watts. Sixth, for the lifespan of the CubeSat, we expect it to last longer than 120 days. However, it is highly dependent on the launching process and the atmospheric condition at the time. Seventh, we want our single solar cell area should be larger than 10 square meters. And for the environmental performance requirements, it is separated into two parts. The first part is for the launching process. The second part is for after the deployment, which is the condition in the space. So next, I would like to talk about our conceptual designs. From the figures, one could see that it contains 5 spindles, 6 motors. 2 center motors will control the motion of the spindles. 4 other motors will do altitude control. And we will also deploy 4 independent solar cells. Each solar cells will attach to 2 booms. So next, we'll have a look at our module design. One can see from our figure, when the center gears start to rotate, it will cause the outer 4 spindles to move in opposite directions and deploy the booms and solar cells simultaneously. So next, we'll have a look at our configuration of the spindles. So each spindles will deploy 2 booms. And after the booms and the solar cell have been deployed, a reserve hole for motor connection will expose on both the boom and the spindle itself. So after everything has been all set, the center spindle will start to work. It will deploy 4 motors and connect them with 4 outer spindles in order to do the altitude control. And the picture on the left is the zoom in of the center spindle and how the other 4 motors gonna move. So next is the deployment demonstration. So once the CubeSat deploy the solar cells, each solar cells will be able to rotate and do the altitude control. So I would also like to talk about our power function system. So this is the power function system of a CubeSat. For a typical CubeSat, which equipped with our deployment subsystem, it should have at least 5 subsystems. First, control, command and data handling. Second, radio frequency communication. Third, altitude control and determination. Fourth, power system. Last one, of course, you need to have a deployable mechanism actuation. And for our project, we just need to focus on power system and the deployment subsystem. So the next slides will go into more detailed block diagrams. So since for our power system, with only 1 battery which only store 100 watts-hour of energy, it is definitely not enough to support the whole mission. Therefore, our power system needs to collect the solar power and transform it into energy to store it into our batteries. And for our subsystem, we also have a microcontroller, which will take charge of 3 types of batteries, including 4 altitude control batteries, 1 deployment and altitude control transitional batteries, and 1 deployment motor. So For deployment motor, since in the space there are a lot of uncertainties. For example, sometimes when we deploy the booms and the sails, it will get stuck at some points. Therefore, our deployment motor need to coordinate with one torque and motion sensor. So just in case it detects something wrong with it, our motor will be able to move in the opposite direction, retract our booms, and redeploy them again. So next, our team will go over to the trade reviews. Welcome back, Irma.
Thank you, Jason. So I'll talk to you a little bit about the boom deployment methods. We have two optimal methods, motorized or tension. When we do motorized, we do have a lot of benefits of being motorized. We could control the speed, we could control the torque, and we could control the quickness of how fast the boom and sails deploy. As far as tension, the only downside about tension is we can't control it in any way or form. It will release all its energy all at once, and as you can see in that GIF, that sail deploys all at once. There's no way we could control that. And with that being said, I'd like to introduce Benjamin.
Thank you, Vermont. So now I'm going to be talking about a little more about the solar cell itself. So let's start off with the materials. We looked into 3 different types of materials: aluminized mylar, CP1, and mylar again, but this time reinforced with Kevlar fibers. Now, as mentioned earlier, these solar cells are relatively large, so thickness is very important to us. We want the smallest thickness possible, so it's going to be easier to store and less space would be required to store it. So starting with aluminized mylar, it has the smallest thickness of 0.9 micrometers, CP1 with 1.5 micrometers, and mylar reinforced with Kevlar fibers with 2.5 micrometers. And as you can also see, the density of each material is relatively close to each other. Also, as mentioned earlier, the surface of these materials have to be reflective, otherwise it wouldn't be called solar cell. And the reflectivity of each materials is relatively high, which is what we want. So now we're going to be talking a little bit more about the folding methods. We looked into 5 different patterns. Each pattern ranges from easy to hard. Now looking at the membrane strength is affected directly by the folding pattern. So keep that in mind. And mountability just means how easy it is to attach to the boom. And it ranges from high to low, or hard, from easy to hard. Now, going a little more in detail about these folding patterns, starting with folding pattern number 1, it's very easy to stow and is highly compact. The disadvantages is that more tension is required to keep the cell at top. Now looking out to pattern number 2, it's the easiest to stow. So that means there's going to be no problem stowing this whatsoever. Also, the crease lanes aren't parallel to the tension line. So that means more tension isn't required as in pattern number 1. Its disadvantage is that all crease lines converge on one point. This means that the membrane strength is decreased, which is why earlier it was shown that it was medium. Moving on to pattern 3. Pattern 3 solves all the problems that pattern 2 have. Not only that, the 2 bottom corners of the sail are free, making it really easy to mount to the boom. Its only problem is that it's difficult to wrap around the spindle. That doesn't mean it's not possible, it's just a little tough. Now looking on to pattern 4. Pattern 4 has all corners free, making it really easy to connect to the boom. Not only that, it guides the boom deployment. This just means that the boom deployment is going to be very smooth and the unfolding is going to be very smooth as well. Its only disadvantage is that it cannot be wrapped around the spindle. This means that it has to be stored in a small designated area. Now moving on to the final pattern. Pattern 5, its advantage is that it just requires 1 sheet. So instead of 4 small sail quadrants, we're just going to have 1 large sheet sail. Its disadvantage is that it can only be wrapped around the spindle. So unlike with pattern 4, it can't be stored in a small designated area. And now I would like to hand it off to Andrew.
Thank you very much, Benji. Hello, I'm Andrew, and I'll be talking to you guys about a boom system, and at the end, give you guys a summary of our project. So these are the 3 types of booms that's mostly found in the CubeSat system. The first type is the tape spring boom. It is very similar to the measuring tape blade that you guys have all used before. It's a single piece of flexible material that's strong in one plane, but relatively weak in other planes. The second one is a dual tape spring boom. It's just like what it sounds like. It's just two pieces of the tape spring bonded at the edge, sometimes not all the way, and it's relatively strong in both of the planes, but it's going to be significantly stronger in one plane because of the geometry. And the third of them is a slightly newer boom system. It's called the ultra thin boom, and it is again using the tape spring system or the tape spring material, but bonded only on one edge and usually on the top. And it gives a relatively good stiffness in most of the plane and also in torsion. All three of these systems would have a possible chance of binding and then misalignment during deployment, although binding can be slightly different with a different design. So here are some of the challenges that we'll have. So we were testing some of the dual tape spring boom, and as you can kind of see, we're about 10 centimeters in, and we're having binding issues already. There's no way we're going to be able to bind it any further. On the right-hand side is a ultra-thin composite material, and they have joined these two materials together with some sort of like a polymer sleeve. So once deployed, it will be able to hold the shape of the boom while allowing the tape spring to slide within each other, so that you won't have any binding issues. So you can also wrap that up in a smaller package as well, which is going to be beneficial for us. So since we don't have ultra fancy composite booms, what we're using is some of the tape springs or measuring tape, as you can kind of see. So in the industry, or one of the industry leaders, what they do is that they use a self-deploying locking mechanism. When it's stowed, it's completely flat, but once deployed, it self-locks together and provide extra stiffness. We're exploring different ways of trying to stiffen this boom up right now, and we'll see what we can get with that. So for the summary, we will design and build a prototype solar sail system that will be able to be stored in a CubeSat unit. And second, we'll design the deployment unit to allow the solar sail to be deployed in a reliable and controlled manner, so it won't damage any of the mechanism during deployment. And third of all, we'll design our solar sail system to be able to integrate with the attitude control system. And we're open to any questions that the audience might have. Thank you very much.
So let's go back to where you were first describing the different mechanisms for. Okay, fine. You indicated that the tape spring booms, that there was no way to control it. Is that what you said?
Oh no! I said it's weak in one plane. So as we try to demonstrate with the little picture right there. So when you take a tape measure out, it's relatively strong.
I was getting actually, there was a prior chart where you had talked about motorized and
so this one, this is the tension.
Right. So you said that something was uncontrollable.
Yeah.
Oh,
When you the module right here for the K7X, right? That's the picture right there. When they released it, they didn't have a form of controlling the deployment. So it was an all-at-once energy that was released because it's a coil that's wrapped around
I
inside.
understand.
Yeah.
It's similar, the motorized one, it works similarly, but there are things to help control the speed of it. So it does also work because, of course, when you roll the booms up, there's a lot of strain. So, once you start releasing it, it starts uncoiling, but it just has a motor and different things to help deploy it smoothly versus just relying on tension. It will just come out without any external forces to keep it.
I understand. But you could, you don't have to, it doesn't have to come out at full speed, right? You could put some sort of a dash pot, something that slowed it down, right? And which way are you advocating then going?
Going into the motorized.
You're gonna go.
Yeah.
Okay.
Oh, a couple questions, all right. Geez, every briefing we've had today, you know, I give them high scores, and then you guys walk in, it's like the Olympics, you know, like, oh man, now we've seen the backflip and the, you know, the triple throw. I mean, you guys are immaculate. Everything you're doing here is just really, really well thought out and well done. I can tell you know everything about this. I just got a couple questions. How do we actually rotate those paddles? I wasn't quite sure I saw that.
Okay.
I think you had it, Jason, at the beginning. There you go. Is there another?
Yeah, so you can see like from this one, the motor will keep extended. So for our platform, it is separated into 5 parts. So it could like be movable, and once it's separated from our model plate, you can start to like rotate by using this motor over here.
Oh, that little. This is the motor right here.
Correct.
These are the 4 motors.
Correct.
So they're going to react to the tape string here, right?
Yes, it will be deployed by the tape spring, by the spindle, and we also will design the track so the motor will not like rotate by itself.
Oh, okay, that makes sense. I'm just thinking that, you know, tape spring is really soft in torsion.
Yes.
We might have to do something more sneaky there to give us some torsional stiffness. We want to get pushed out, that's a good thing, but we also got to get torsional stiffness somehow as we push out. So there might be a way to have that being a tube. I mean, that's the tube you're talking about, Andrew. I don't know, but that might have to be not a closed section, but it might have to be a locking section, because now locking section can give me torsional stiffness. But a single channel, that's really soft in torsion.
That was the geometry. There are tricks where like as it unfolds, you know, a thing might drop out or spring loaded, so kind of close the geometry off.
Mm-hmm.
We need to explore on that. We just got a water jet thing up and running. They were training last night. I've been eyeing that thing for a little bit.
Yeah.
So we hope to get some stuff cut and hopefully have some sort of self-locking mechanism for it.
And also, like, for instance, they might have self-locking mechanisms, but some they might not have a self-locking mechanism, but they're rolled up flat, but then they have one on the exit side, there's a guide so that they kind of curl in, so they almost form a tube.
Yeah, that's what we want.
Yeah,
we want
so it's
we
a
want
bit
that tube.
stronger than
Right.
just
Yeah.
like concrete.
Yeah, we want, if we can somehow get a closed section with blocking interfaces, really, that'll give us a lot more torsion stiffness. And then, sorry. So,
yeah, also since this one, it's just to connect so that it can kind of extend a little bit and be able to rotate. They don't have to be extremely long like the booms for the sails.
I see.
So
Maybe
there are
a couple
some,
inches in.
yeah, only a couple. So there are potential other types of booms, perhaps that we could use because
No, that's a good idea.
yeah, because they don't need to necessarily be that long.
I wasn't sure how far they came out. Yeah. And those little motors would be something we steal off of the camera, or we had to buy those motors, I guess. I don't know.
Yeah.
There's the little gear motors, I guess.
Yeah.
We don't have to move fast.
Nope.
We want a little bit of torque out of it. So we have to run out a little bit of harness out with them too, then probably. That should be doable. Yeah, I like you guys' ideas. I think you're being really innovative, and you kind of have to be on this one. It's really, really interesting. Are you planning to? Oh, sorry. Go ahead.
Yeah, I was saying when we call these companies for samples, whatnot, and they're like, yeah, a couple $100,000, and yeah, if you got a design, we'll get you going. We'll design a whole shebang for you. And we're all like, oh, okay, we got about $300.
Yeah. There's a lot of folks out there that are kind of hungry right now that would love to have a piece of this if we had the money to go with it. Are you planning to build a little subscale test bed or something like that?
Yes, we will.
Okay. Do we need a area for that? Are we going to try to put it on maybe a flat table like that, or do we need a big floor to put it on?
Like a flat table. I think our lab would be too small, so we'll be eyeing around for like a nice flat area where we can use the floor as like sort of like a lot of the solar sails we have seen uses a floor to kind of like just balance everything out, because nothing is super heavy, so we're not worried about resistance in this plane, but it just can't support itself once it's deployed.
Right.
Oftentimes they have a table with a small hole in the center, or I mean, it doesn't necessarily have to be, but basically for the CubeSat to be so that the boom can lay flat against the table. But of course, since there is some height before you get to the boom, they have just a little hole that it can kind of sit